Welcome everyone. In this video lecture, we will solve a GET 1998 question which is based on mass action law. So the question is the electron and hole concentration in a intrinsic semiconductor are Ni and Pi respectively. The hole concentration and the electron concentration are Pi and Ni respectively in an intrinsic semiconductor, and if the intrinsic semiconductor is doped with a p-type material, these change to N and P respectively. Then we have to identify which is the correct answer. N plus P equals to Ni plus Pi, N plus Ni equals to P plus Pi, Npi equals to Nip, and Np equals to Nipi. So first of all, we have to know the law of mass action. So basically, this is a very basic in electronics. So law of mass action is nothing but simply we know Np equals to Ni square. Generally, we know this one formula. Np equals to Ni square, where we can say that this law of mass section is the product of free electron, that is our N, and free hole concentration. Okay, thus this one is the product of free electron concentration and free hole concentration, of free electron concentration and hole concentration. Okay, which is equal to a square of the intrinsic concentration. Intrinsic concentration, we can say the intrinsic carrier concentration better too. So this one is Np equals to Ni square, because this one is important. If you know this one, this N is nothing but simply free electron concentration. Okay, this P is the free hole concentration, and this Ni is our intrinsic carrier concentration. Okay, and this equation is valid. This equation is valid for both intrinsic as well as extrinsic semiconductor. So this one is valid for both intrinsic and extrinsic. So if we have to write for the intrinsic semiconductor, we can simply write N into P equals to Ni square. Now I am writing Ni square. Okay, because in this question they have given electron and hole concentration as Ni and Pi. So we can replace this N with this Ni, and Pi equals to Ni square. Okay, that's why I am writing this as a Ni square. Because if you write again a small Ni, there should be some confusion. So this one is the for the intrinsic. Now for the next one, we can say the extrinsic semiconductor. This one, extrinsic semiconductor. For the extrinsic semiconductor, it may be our what, N-type material. Okay, and one, it may be our P-type material. Okay, so in case of N-type material or N-type semiconductor, because this one is a extrinsic, so we can write as N of N into P of n, or we can write this as a Ni square. Now for the P type, we can write as n of P into P of P equals to Ni square. Okay, I'm just writing as a Ni square because in the question it is given Ni into Pi, so that's why we are not writing intrinsic carrier concentration as a Ni square. So, and all this thing is happened under thermal equilibrium, and this one will be under the thermal equilibrium. Okay, and this n of n, this n represents the suffix. This suffix n relates n type. This one is n type. That's why n of n, p type. So n of p. Okay, this suffix relates the n type and here p type. So now at the both the all the intrinsic carrier concentration will be same. So in our case, for the p type material, for the p type material, okay, so this one is p-type material. For the p-type material, they have given the electron concentration Hn. So I am just writing this as a N, because in question they are saying p-type electron concentration is N, then into P equals to, simply we can write Ni square. So if we consider these equations, say this one is equation number 1, and this is our useful expression 2. So if we think about these two equations, what we observed that Ni into Pi equals to Ni square, okay, and this one is also equals to N into P. This one from equation 2, and this one from equation 1. Okay, this one is the important thing to establish the relationship. So directly you can say this one is nothing but simply NiPi equals to Np. So this one will be the correct relationship between the carrier concentration of electrons and holes in intrinsic one is equals to the carrier concentration of electron and hole in the p-type material. So we can simply say this Ni, okay, this NiPi, this NiPi, and this one is our Np. So this NiPi is nothing but simply the product of electron and hole carrier concentration in an intrinsic semiconductor. Okay, and this one is our nothing but simply the product of electron and hole concentration in a p-type material. Okay, so this product will be always same in thermal equilibrium. So NiPi, if this one is our n-type, so if this one is n-type, so this one is also be our n of n, p of n, and this one is n of p, p of p. So this one is a very important NiPi. Okay, NiPi equals to this one. So the correct option for this question will be our option number D. The product of the carrier concentration of electron and holes in a p-type is same as that of the intrinsic one. Intrinsic carrier concentration, intrinsic semiconductor, n concentration, electron concentration, and hole concentration. So this is the correct answer for this question. Okay, so this is a simple one, but we have to know this fundamental law of mass action, product of the free electron concentration and hole concentration is always equals to Ni square. In the question, it is represented Ni. This one is small n subscript I square. So again, in intrinsic, they are saying we have to take care of Ni and Pi. So that's why I'm writing Ni, Pi, and we have replaced the this one as a capital Ni square. Okay, so it is just a symbol. So this is all about this question. So thank you for watching this video.